Hello student, myself Professor Ashok Kumar and I am working in Department of Mechanical Engineering at Dr. Subhash Technical Campus. Dear student, today's video lecture in which especially we will discuss on chapter number 8, Shaft and Key, part 2. Basically this chapter, as you know, that comes in subject fundamental of machine design, which is specially coming in 4th semester degree mechanical engineering. If you have seen my previous video lecture on same chapter, at that time it was the part 1, and I have discussed only about key. That particular video lecture I have discussed about an introduction, types of key, various types of traces that are being produced in key, and at the end we have also discussed about the design of key. So particularly this lecture will cover about shaft, various traces that are produced in it, and the design of shaft based on various criteria. Before starting and designing the shaft, let's have an introduction. Basically, a shaft is a rotating machine element which is used to transmit power from one place to another. That means, suppose you want to have the power transmission from one place to other place. If you are finding any rotating machine and it is helping to have the transmission from one place to other place, it will be known as a simple shaft. Generally, we know that shaft is used basically for the torque transmission, and for the torque transmission, we know that we require tangential force and of course the perpendicular distance. So suppose that you have given one circular shaft and there is a one tangential force, like tangential force F is acting, and if the distance, or we can say that the radius, that is R, so ultimately by multiplying both of the terminology we will have the torque, and that is transmitted by shaft. So ultimately power is transmitted by virtue of force and torque. Only shaft is not responsible, or with only with the help of shaft we can never transmit power, but we require some additional elements also. We have seen that on shaft some rotating member like gears, sprockets, pulleys, and much more components are being mounted over the peripheral surface of shaft, and once you are rotating shaft, gear or pulley so mounted are get rotated. So ultimately we can say that the shaft outer surface or peripheral surface of shaft rotating members are required, which in turn help to transmit power from one place to other place. Dear student, you have also seen that, for example, let's have a very simple example of our workshop wherein lots of machinery required power, and all that power comes from the driver. Driver, that means, suppose you are taking an example of lathe machine, and we all know that in lathe machine there is an electric motor, and whatever the power, or we can say that the torque required to perform various operations through lathe machine, it will be delivered through this an electric motor. So over here an electric motor will be the driver source of power, whereas the tool post, or we can say that the lead screw, uh, that will be the driven, or we can say that end user power. So ultimately, in that particular case, you require to transmit power from an electric motor to the driven end. So you may have seen that there is a chain drive. We can say that there are a gear drive, there are pulley drive, and so many. So this is what about the power transmission through shaft. Generally, it may not happen always that the shaft has regular circular cross section, but in some cases you may also find that it has square, or we can say that other types of cross section are also there. Now, after that basic and introduction, let's have the discussion of types of shaft. There are basically two main types. One is transmission shaft, another is machine shaft. From this name, one can easily understand the function of each and every shaft. Over here, Transmission shaft, if we are talking about transmission shaft, it transmit power from source to the machine. That means what I have discussed, an example of an electric motor and lathe machine. And for that line shaft, counter shaft, main shaft are few examples that are being used in workshops, factories, or some other places. If you are finding such kind of shaft, then it will be uh, responsible for power transmission from a driver to driven. So this is what about the transmission shaft. And one more thing that we should to discuss here in about transmission shaft is that we all know that transmission shaft used for the transmission of torque as well as power. So suppose you have any transmission shaft and outer surface of the transmission shaft. Suppose you are mounting pulley or gear or whatsoever other rotating elements for the power transmission. Due to power transmission, due to tangential force, due to self weight, these transmission shafts are subjected with two basic criteria. One is twisting or torque, another is bending moment. So ultimately, we can say that transmission shafts are always subjected with twisting moment as well, a bending moment. Now, after the transmission shaft, there is a machine shaft. Look at the diagram. uh, Machine shaft, that clearly means that it is an integral part of machine itself. For example, suppose in IC engine there is a crankshaft. So crankshaft is integral part of that particular machine. So we can say that it is machine shaft. Similarly, crankshaft, which is being used for the opening and closing of exhaust and inlet valve, it is also a kind of machine shaft. So this is the machine shaft, which is integral part of the particular machinery that we are using. Now, after the discussion of various types of shaft, let's have the few permissible traces that is very much useful for designing of shaft. So, according to ASME, American Society of Mechanical Engineering, uh, uh, it has clearly defined the stress limit of particular shaft. So, for example, suppose if you are designing a shaft based on compressive stress, so just you have to take care the maximum or permissible limit of that particular shaft. Over here, ASME has specified that 112 megapascal is the compressive permissible stress you should to take, but whenever there is a no keyway, that means shaft uh, over an outer periphery of which there is a no slot for the keyway. So particularly there is a perfect, if there is a perfect solid shaft, then and then you can say that this shaft is without keyway. And at that time, particularly the permissible or allowable stress limit for in compression failure should be taken as a 112 megapascal. Suppose your shaft being mounted with some rotating members like gears, pulley. At that time, you need to have the keyway on outer surface or outer peripheral surface of shaft. So at that time, maximum compressive failure you should to take, or maximum compressive limit in particular uh, the cases where the keyway is available, that is 84 megapascal you should to take care. But for definite or specific condition, there is a strict relation that is given by ASME. Suppose you have any material and it has some elastic limit, or we can say that yield limit. So while designing in tensile or compressive failure, you should to take it is a 0.6 into that permissible elastic limit. Or you may also calculate like 0.36 into ultimate stress of that particular material. So out of that two calculation, you have to select which has the less value. So this is what about the compressive tensile stresses, particularly that should be taken as a permissible stresses in shaft. Now, second types of stress that is has a very vital role while designing the shaft is shear stress. So suppose you are using a shaft without keyway, At that time, the permissible shear stress should be taken as a 56 megapascal, and if you have the shaft which has a T slot, at that time the permissible shear stress that should be taken as a 42 megapascal. Once again, there is a specific or definite condition that ASME has given. Suppose you have material of shaft and the ultimate, or we can say that the yield strength or permissible limit that you have given at that time, your stress or design stress should be 0.36, 0.3 into sigma elastic, or you may also calculate by 0.18 into sigma ultimate. So out of two calculation of stress, shear stress, you should take it as whatever the less amount you should to take it as. Now, after that, the discussion of the permissible shear and compressive stress, let's have the design of shaft. Basically, shaft is designed based on two criteria. One is strength and other one is the rigidity and stiffness. Over here, while you are designing a shaft based on strength, just at that time, you have to take care of twisting moment, bending moment, combined effect of twisting and bending moment, and also you may also consider axial load in addition with the torsional and bending moment. So there are basically, if you are designing shaft based on strength, you have four criteria to design. One is you may design your shaft based on purely twisting moment, based on purely bending moment. You can also, suppose you are finding that the shaft is having the multi-loading actions, and that means it may possible that your design or your shaft may be subjected with bending and twisting moments. You should to take care of the combined effect of both of. So at that time, option number 3 you should to select. And suppose there is an instant where all this combined effect with along with the axial load is also acting. At that time, you should to take care of the design criteria 4th in case of the strength design. Let's have the design, and that design is specially based on design of strength. We will first discuss on design of shaft based on strength, and then after we will discuss design of shaft based on rigidity. So over here, suppose you have given one shaft over which there is one torque is to be transmitted in clockwise direction. There is an axial force P is acting through CG or neutral axis of that shaft, and one lateral load F that is acting on outer peripheral surface of the shaft at the end of it. So in that particular case, if you are looking carefully, then basically there are three criteria. One, you should take care of torque. That means it is responsible to have the twisting moment. One is the lateral force, which cause the bending moment produced at the friction over here. So you have to also take care of bending moment too. One more thing, that is an axial load P that is also acting. So you have to also take care of axial load too. So in previous my slide, we have discussed the design of shaft based on strength. There were four basically sub criteria. So all that four sub criteria, in particular this case, you have to focus upon. So let's have the design of shaft based on strength. First of all, you should to take care about the twisting moment, and we know that there is a very famous equation, torque equation, like that: T upon J is equal to tau upon R. Over here, T is the twisting moment, J is a polar moment of inertia, tau stand for the shear stress that is being produced while transmitting power and torque, and R, that is the radius of shaft. So by putting the value of polar moment of inertia and R, that is equal to d by 2, and solving that entire equation, ultimately you have the torque is equal to pi by 16 into sigma b into dq. So this equation is specially and particularly based on design of shaft based on twisting moment. Now suppose you are concentrating shaft design based on bending moment alone. At that time, just go through bending equation. M upon I is equal to sigma b upon y. Over here, M stand for the bending moment, that what we have discussed, that the bending moment is produced over here. So this is the capital M bending moment. I, moment of inertia, sigma b, that is the bending stress, and y is equal to distance of neutral axis from the extreme fiber. So by putting all that relevant value in this equation and by solving it, at the end you will have the bending moment M is equal to pi by 32 sigma b into d cube. So this is the relation where you are designing design of shaft based on strength, particularly focusing on bending moment. Then after, suppose, as what I have said earlier, in some specific cases, you have to take care of combined effect of twisting and bending moment. So at that time, you have to refer the criteria number 3, and that is shaft subjected to combined twisting and bending moment. So for that, as we have already discussed in previous video lectures, that if a combined effect you have to take care of, just go through failure theory. So there is one famous theory, and that is the maximum shear stress theory or Guest's theory, and which is used specially for the ductile material. So over here, according to maximum shear stress theory or Guest's theory, tau max, that means maximum shear stress, is equal to 1/2 under root sigma b square plus 4 tau square. So just you have to put the values of sigma b over here and tau over here from the previous slide. And by solving and simplifying that relation, ultimately you will have the equation 32 upon pi d cube bracket 1/2 bracket m plus under root m square plus t square. So this is what the design of shaft based on a combined effect of twisting and bending moment by maximum shear stress theory or Guest theory. One more famous theory of coming from the failure theories is the maximum normal stress theory. And according to maximum normal stress theory, sigma b max is equal to 1/2 sigma b plus 1/2 under root sigma b square plus 4 tau square. So just you have to put the value 1/2 sigma b square plus 4t square over here. And just by solving it, you will have the 32m pi d cube bracket 1/2 m plus m square plus t square under root. Basically, sigma b, that is equal to 32 m upon pi d cube, and that is taken from the bending equation. So this is very simple to understand and design based on combined effect of twisting moment and bending moment. Suppose shaft is subjected with fluctuating load. At that time, you should to go for the effective twisting moment and effective bending moment. Suppose that there is a one shaft which is subjected with continuously fluctuating in load. That means load is no remain same throughout the operation or some specific periodic time. So at that time, you just need to calculate effective twisting moment as well, effective bending moment. And for that, over here, effective twisting moment is equal to under root km square plus kt whole square me 1/2 bracket km into m plus under root km m square plus kt t square. Over here, km and kt both are the constant and depends on the loading conditions. So this is what about the design of shaft based on combined effect. Suppose just you find the shaft where there is a effect of combined loading along with an axial load. So like that, look at the figure. There is an axial load acting over here also, and you have to take care of twisting as well as bending moment. So at that time, you have to just go through bending equation m upon I sigma b upon y. From this equation, kindly convert this equation in terms of bending just like that. And by putting all that value, m that is equal, y is equal to d by 2 and I is equal to pi by 64 d raised to 4, and solving it, you will have 32 m pi d cube. So this is the combined effect. From the combined effect, you are getting bending stress. And we know that due to axial load, either it may be the tensile or it may be the compression. You will have the direct stress, and direct stress is equal to force upon cross-sectional area or perpendicular area. So by putting that value over here and by solving it, you will have the 4f upon pi d square. So this is the case where you should to take care of combined loading along with an axial load. So in that way, you can have the easily design of any shaft. Now, along with that design of shaft based on strength, look at the diagram very carefully. There is a shaft and which is subjected to various loading and various moments. Look at the diagram first. There is a one shaft that you have given which is subjected with the torque at the both of the end, which is acting in opposite direction. Transverse load is also acting. Axial load is also acting. So this is the case number 4. It becomes case number 4 where you should take care of all the external loading and moments. So over here we have calculated direct trace, we have calculated combined trace. So just sum up both of the kind of traces over here and solve it. You will have the equation of trace, and that is equal to 32 m1 pi d cube. Over here m1 stand for m plus f into d upon 8. So this is the criteria number 4 under the design of shaft purely based on strength. Now, after strength criteria that we have designed, one more criteria that we have already discussed in previous slide, that is the design of shaft based on rigidity and stiffness. It clearly means rigidity, that means it is the design based on against deflection. So suppose you are using any shaft as a design engineer, you should have the sufficient idea that your designed shaft should not deflect anywhere. So if you are considering that part, that criteria and designing the shaft, it will become design of shaft based on rigidity and stiffness. Rigidity, it means the capacity or material property against the deflection due to the external force. For that particular criteria, so it is very much important in case of crankshaft in IC engine, because we know that in IC engine, crankshaft is subjected with fluctuating loading, and it may possible due to high torque and power transmission. After few periodic time, it get deflected. So in case of IC engine, you should to design your crankshaft based on rigidity and stiffness. Now, for example, if you are taking and designing IC engine crankshaft, the maximum permissible limit of the deflection should be 0.25 degree. That means uh, beyond or above the 0.25 degree, your crankshaft of IC engine should be not deflect anywhere. This is the pure and perfect design based on rigidity and stiffness. Suppose you are taking an example of line shaft or transmission shaft being which are being used in factory and machinery or machine shops. There is also specific limit, and limit is 2.5 to 3 degree per meter. So this limit should be not crossed in a way of deflection by the transmission shaft. So based on that rigidity and stiffness, any shaft that you require to design should be like that. Just go through torque equation and convert this equation in terms of the angular deflection, because this design is purely based on deflection theta. So we require to have the deflection value, and from this torque equation, convert this equation in terms of angular deflection theta and put the relevant value over here and simplify it. You will have a relation for theta, and that is purely based on rigidity and stiffness design criteria. After designing shaft based on strength and based on rigidity and stiffness, let's have few examples to solve. Example number 1, that is you have given a line shaft and rotating at 200 rpm, and it transmit power 20 kilowatt. The shaft is made from the mild steel, and permissible shear stress that you have given is 42 megapascal. Just you require to calculate a diameter of shaft. But one more thing that you have to focus upon is that you have to neglect the bending moment, in particular this example. So over here, there is only one case that you require to consider over here, because bending moment is you have to neglect the bending moment. So ultimately, first of all, kindly calculate the torque transmitted by this shaft. and that is equal to from 2 pi nt divided by 60, one can have easily calculation of torque. So by putting that value over here, you will have the torque 955 Newton into meter, ultimately 955 into 10 raised to 3 Newton into m. Once you are calculating torque, putting that value of torque is equal to pi by 16 tau into d cube equation, and solving it, you will have the diameter like 48.7 mm, or nearby equal to, it becomes 50 mm. So this is the example number 1 in which we have calculated diameter of shaft. Second example that you have given, one shaft that is subjected to bending moment of 3000 Newton into meter, and it transmit torque is equal to 10,000 Newton into meter. A shaft material is also given. 45C8 steel is the material of shaft, and the tensile stress or permissible tensile stress is 700 megapascal you have given. Permissible shear stress is also given is equal to 500 megapascal, and factor of safety that you have to take care of 6. Just by using that particular data, you require to calculate the diameter of shaft. So first of all, before solving this example, kindly look at the factor of safety that you have given, and along with that factor of safety, you have also given ultimate shear stress as well as ultimate tensile test. So first of all, you should to convert this ultimate shear and ultimate tensile into permissible range. How? It's very simple. Just by divide that ultimate shear and compressive stress with factor of safety like that. So over here, ultimate tensile test is 700, factor of safety is 6. So ultimately, permissible tensile test is becomes 116.7 Newton per mm square. Similarly, you can also use the same relation for the calculation of permissible shear stress, and that is like that. So permissible shear stress will become 83.3 Newton per mm square. Now, as you know that over here the case is of fluctuating the loading. That's why you have to calculate equivalent twisting moment. And we have also seen in previous slide that equivalent twisting moment is equal to under root m square plus t square. By putting that value, you will have the equivalent twisting moment is equal to 10.44 into 10 raised to 6 Newton into mm. Once you are calculating twisting moment, there is also one relation for twisting moment, and that is Te is equal to pi by 16 tau into d no d cube. So on the left hand side, just put the values of twisting moment that we have calculated in previous slide, and by equating both of the relation, you will have the diameter is equal to 86 mm of shaft. Now, if you are designing based on maximum normal stress theory, you should to go for the equivalent maximum bending moment, and the bending moment equivalent bending moment relation is that the 1/2 m square plus t square. Ultimately, this will become equivalent twisting moment that we have already calculated. Put that value over here, and by solving that relation, you will have the equivalent bending moment is equal to 6.72 into 10 raised to 6. We also know that from the bending relation, equivalent bending moment is equal to pi by 32 sigma b into d cube. So by equating both of the relation, by putting that relation of equivalent bending moment over here and equating both of the relation and calculating diameter of the shaft, then it will become 83.7 mm. But over here we have calculated diameter of shaft based on two theory. Look at the previous slide. Over here, we have calculated based on maximum shear stress theory. Over here, we have calculated maximum normal stress theory. So over here, ultimately, you have the two value of diameter of shaft. One is 86 mm, and other is equal to 83.7 mm. So as a design engineer, you have to select larger of two that you have calculated values. So larger value that comes from the 86 mm, that is your finally design diameter of shaft. So dear student, this was the few example at the end of my video lecture. This video lecture typically we have covered especially design of shaft, types of shaft and introduction of it design criteria based on strength and rigidity, and at the end we have solved two examples based on that. Still you are finding any difficulty or having any query or questions, let me inform, kindly come to me, we will have the solution. Thank you for your patience for my video lecture attendance. Thank you very much, and kindly stay tuned up because we are uploading numbers of video lecture every day, every time. This is. Thank you very much.